Symmetry, we know what symmetry is. Symmetry is a property illustrated when the image of a transformation of a figure coincides with the pre-image. It's a fancy definition of symmetry. We know that when we have symmetry, especially the traditional symmetry that we know, we're looking for a line that splits a figure in half that we could fold it over. So essentially, okay, symmetry in this sense is if we were to reflect this figure over this line, it would still be the same figure. We're going to see that the transformation does not have to be a reflection. I know that's what we think of. We think of reflecting it. We're also going to see rotational symmetry today too. So, identify whether each figure has a line of symmetry. If it does, draw the line of symmetry here. A heart, we know since kindergarten, we've been drawing lines of symmetry on hearts. We could draw that line straight down the middle, just like that. This trapezium here, I do not see any lines of symmetry. It's close to being a line of symmetry there, but that is not going to work. There's no line symmetry there for that one. Now we also have rotational symmetry. Rotational symmetry is a type of symmetry which describes that a figure can be rotated about a point by an angle less than 360 degrees so that the image coincides with the pre-image. The smallest angle through which a figure can be rotated in order to coincide with itself is an angle of rotational symmetry. All right, so let's take a look at this. It says, well, first we want to rotate RST 180 degrees about point R. There's RST, we want to rotate it about point R. If we rotate it, it means that angle T is now, or T prime would be right there. R prime, of course, would not change. And then S is going to be out here somewhere. So that would be our image once we rotate this about point R. And now it says, does the new composite figure have symmetry? So this whole thing right here is our figure that we're looking at. Does this have symmetry to it? Well, it doesn't have line symmetry, but it does have rotational symmetry. If we rotated this entire object about point R, it would coincide with itself after we rotate it 180 degrees. It doesn't matter if we rotate it counterclockwise or clockwise, it would coincide with itself. It would be the same image. So yes, it does have rotational symmetry. Does it matter if we rotate it? No. Just as long as we rotate it 180 degrees. If we rotate 180 degrees, it's going to coincide with itself. Yeah. Here says the order of rotational symmetry is the number of times a figure with rotational symmetry coincides with itself as it rotates 360 degrees. A square here has rotational symmetry of 4. 1, 2, 3, 4. As it goes 180 degrees, it would coincide with itself 4 times. The order of rotational symmetry is equal to 360 degrees divided by the angle of rotational symmetry. So that may make it a little bit easier on ourselves just as we check to make sure it all makes sense. The order of rotational symmetry is equal to 360 degrees divided by the angle of rotational symmetry. All right, it says tell whether each figure has rotational symmetry. If so, give the angle of rotational symmetry and the order. Well, this N, if I rotate it 90 degrees, I don't get anything. If I rotate it 180, this end of the leg would kind of line up with that one, and it would coincide with itself. So yes, this does have rotational symmetry. 180 degrees it takes to coincide with itself for the first time. 360 divided by 180 is 2. The order would be 2. As we go 360 degrees, 1, 2 times it would line up with itself. This next one here, this is practically a square for us. As we go 360 degrees, 1, 2, 3, 4 times it would rotate and line up with itself. 1, 2, 3, 4. And so yes, this once again has rotational symmetry. Every 90 degrees we rotate this, it would coincide with itself. So that means the order is 4. This last one right here, if we start rotating it, well, once we rotate it up, then the pointy end is going to be up here. That's 180 degrees. And when we keep turning it, in order for it to just coincide with itself again, it has to rotate 360 degrees. That's any object is going to work every 360 degrees. So we do not consider this rotational symmetry. No rotational symmetry, which means it doesn't have an order. So, no rotational symmetry. Great. Finally, it says tiles often have many lines of symmetry, so they can fit easily into patterns. How many lines of symmetry does each regular polygon with up to 10 sides have? Well, let's just start with a triangle. This is an equilateral, equiangular triangle. We have a line of symmetry right there. We have a line of symmetry there. We have a line of symmetry there. That's because it's equilateral, it's equiangular, it's regular. So there's 3 lines of symmetry on a triangle. If we look at a square, we've got 1, we've got 2, we've got 3, we've got 4 lines of symmetry on a square. On a pentagon, we've got 1, 2, 3, 4, 5 lines of symmetry on a pentagon. If we kind of see this pattern, 3 lines of symmetry on a triangle, 4 lines of symmetry on a square, 5 lines of symmetry on a pentagon, they have the number of lines of symmetry as the number of sides that they have. So a 15-sided tile has 15 lines of symmetry. Yeah. Feel good about that.